Hello everyone and welcome to Chapter 8. Today we're going to be talking about how to estimate population parameters. So just as a reminder, a population parameter is a numerical value in our population we might want to know about. Maybe you want to know the average age of your customers. Maybe you want to know what proportion of your sales are from new customers. These are just some sales examples. Obviously, it really depends on what you're interested in knowing. But no matter what, we're looking to describe a big group and just one characteristic of that big group. That's why this says single. Get the idea? So here's some of the outcomes we're going to be looking at today. So we're going to talk about the difference between a point estimate and a confidence interval. We're going to construct two different types of those using two different types of distributions. And in particular, we're going to be talking about two different types of data. Quantitative data, which we can do means of, and then qualitative data, which we can do proportions on. So there's going to be the theme going all the way back to like the first thing you learn. Hey, what are the two types of variables we've got, or the two types of data that we've got? It's important to note that I'm going to be using a significant amount of sampling distribution stuff in this. So if you haven't looked back at the stuff from last week in a while, you might want to take a quick peruse through your beginning part of your notes for that, or even just like a little summary from the chapter itself on your textbook, just to make yourself familiar with some of the things I'm going to say. All right, so first let's start talking about a point estimate. So a population parameter is going to be a single value from our population. We've been using population values for those for a while, so you're used to a population mean as being mu or mu, depending on how you pronounce it, and then a population proportion, we just use a p. So these are going to be values about big groups that we're interested in. And usually if we want to sample and like describe that using just a single value from a sample, then we'd be using a sample mean to describe or try to estimate the population mean. And the same thing can be done with a sample proportion. We try to use that to estimate a proportion. And we've talked in the last chapter about doing sampling error. That's just the difference between those two. And we keep in mind that every sample is going to have a different sampling error. So is using one sample going to be sufficient enough for us to be able to tell what's going on? Maybe, maybe not. All right, so that's another big thing. You draw one bad sample and like you're going to have a big error, and that's problematic. So what we want to do is we want to find a better way to estimate this. So when I thought about this as a student, I had a lot of confusion on why we would bother with this. So I have a stupid analogy to help you. So pretend we've got like a pond. Enjoy my drawings. This is going to be fun. Here's some water on it. Oh boy. I wish I had a better digital screen so I could draw you better pictures. So somewhere out in this pond is my population proportion. Yeah? Or my population mean. I'm going to do it as a fish. Yes, this is a fishing analogy. So you've got a couple choices for your tools. If I'm going to use a single value or a point estimate, I'm essentially using a spear. And I'm, just stabbing my spear into the water and hoping, do I hit my fish or not? And that's it, because I'm only using one value. So what's going to work better is if we take a spear and we attach a net to it. So we go around that value. Or sorry, that single value, and see, are we going to be close to catching our fish? So what we're going to use instead is we're going to use a net, a range of values to possibly capture our mean. So obviously I failed to do it with my picture right here, but if I would have used a bigger net, I would have been successful in capturing my fish. So what I'm going to show you today is how to create the net, basically, and it's based on samples. So keep that in mind. We're going to gather samples, and we're going to use them to estimate parameters, population stuff. All right, so we start with the point estimate. And what we're going to do is we're going to build a number interval around it. These are called confidence intervals. So what's going to happen with these is I'm going to have an interval of possible values, and I'm going to have some probability that I'm going to possibly gather my population parameter. That chance of me correctly gathering my parameter is called the level of confidence. So that's where that number name comes from. An interval because it is an interval of values. Now some of the notation that this textbook uses for interval is a little strange, but it is exactly like how you describe them back in algebra. So I've got a picture of a number line down here. Well, I should have made this longer now that I'm looking at it. Sorry about that. It'll have some lower end value as your lower end cutoff, and it'll have an upper end value as your upper cutoff. So for instance, how you would have written this back in your algebra days, like say this is 4, there we go, and then this is 8, then dead center in between them would be 6. Then our interval in this case would be from 4 to 8. And if you remember, this is saying it's all the values between 4 and 8. And 6 is in there in particular. And then one thing to notice about these is it's always an even distance apart. They're never lopsided. So this is a distance of 2, and this is a distance of 2. These are just some basic structure things that we're going to get into as we construct confidence intervals. So we want to do this in a probabilistic and data-driven way, not just number line way. All right. So we're going to start with a point estimate, and we're going to move so many standard deviations away. So keep in mind, standard error is just a word that means standard deviation, but for a sample. I'm going to write that on here in case you forgot. Standard deviation. Uh-oh. It thinks I'm clicking. Hold on. There we go. I'm sorry, I'm having some problems. We're going to abbreviate this. Standard deviation, but we've built it based on a sample value, not from a population value, because that's what I've got. I've got a sample. A sample on the sampling distribution. Oh no, this looks like not. I hope that's readable. Anyway, so this is if I build my standard deviation on the sampling distribution from a sample instead of a population parameter. And more often than not, you're going to have sample information, not population parameters. So here's the idea. If you're using your point estimate and your sampling standard deviation to build your sampling distribution, hopefully you've done it large enough to where you get something normal. Woohoo! And then you're just plopping your point estimate down. And then you're saying, oh, well, I want to go so far away. Using standard deviation as your distance, so that I'm pretty sure I am really likely to get my population mean. So we know from the empirical rule, if I go 2 standard deviations away in each direction, that's going to give me about 95% of data. About 95%. So then I would be 95% sure that in this range of values from here to here, I would get my population mean 95% of the time. Now there's a 5% chance I'm wrong, but that's pretty small. So how do I get that? So this lower end is going to be my point estimate, and this is me just abbreviating because I don't want to use symbols here, plus, not plus, 2, minus 2 times my standard error. And how did I get to here? I took my point estimate and I added 2 standard errors. Get the idea? Now, the use of 2 was a bad choice because I was using the empirical rule. The empirical rule relies on the fact that we're estimating to use this. So we're going to be a little more critical or more accurate with that and use critical values instead. And there's 2 different critical values we're going to look at. One is based on the normal distribution. One is based on a new fun distribution that you've never met before, but solves a lot of our problems when we try to do this estimate. All right. First up, don't forget standard error for the mean is based on the idea that I'm going to be doing the sampling distribution. So just as a reminder, this just means spread of the sampling distribution. Now, if you know what the population spread looks like, we can use this value here, sigma, the standard deviation of the population. When you don't, you're going to be forced to use the sample one, or little s. And we recognize the fact is that, well, when you use the sample one instead of the population one, you're going to introduce some error, or it's going to be off by a little bit, as we like to say. Remember, errors aren't mistakes, it's just how far off you are. When we do this, this is called standard error. We haven't done standard error for a mean yet, we've only done it for a proportion, but it still exists. So if I don't know sigma, this guy right here, I'm going to be stuck using S, aka if I'm stuck with I can't know what my population spread looks like, I'm going to be using the spread of my sample instead. And that'll introduce a little bit of error, but again, we're estimating. We are expecting to be off by a little bit. Alrighty. Let's talk about levels of confidence. So if I'm using the standard normal distribution, I can figure out my critical values. So these are what are called critical values because they're the values that's associated with the central probability of a certain confidence level. I did not leave myself enough room to draw a picture here, so I'm going to try to draw it at the bottom. So basically the idea is if I look at the standard normal distribution, which has mean 0 and standard deviation 1, and I go out to, so I'm going to do 95 because it's the most common one, 1.96, and it's negative twin, negative 1.96. This area in here will be 95%. Oh, I wish it would let me change colors. Fun times. And then the rest of these values are found similarly. So notice that like 80%, around 0, is a little bit tighter and closer in, 1.28. I have seen 80% used, but not really. So that area in the middle is 80%. So this harkens back to us doing central or middle probabilities back in our Minitab adventure days back in chapter 5, if you remember that. So that's how we're going to get critical values every time. Now, you'll see in the Minitab lesson videos this week that you will not need to know these if you're planning on using Minitab. Minitab will automatically calculate them for you once you tell it what you want it to do or what confidence level you want. So you just have to be careful at that step. There was something else I wanted to say about this. Come on, brain. Nope, that was it. Okay, I'm wrong. I will always give you a table of these values because honestly, it's just a waste of time to make you look them up. You would just look them up anyway if you were working anyway, or using this for work rather. So it's very important that you notice this top up above. Hey, when I know sigma, I know my population will look normal. Or if I know my population is normal, I can do this. There's going to be cases where I can't do that. All right, so around 95%, as we've already said, gives us 1.96. This is the most common and popular, I wish I wouldn't have written that so high up, sorry, value or critical value. So the other notation for this is we'll also call this, and I have a bad habit of doing this, this is an old notation, is Z star for critical values. They're just a specific Z value known for producing a specific known level of confidence, and they always go with a center probability and not a left or a right or anything like that. It's always a middle. All right, so let's suppose you gather 4 different samples and then you do the area of confidence around them. So if you look on here, I've marked the true mean. So what I want you to see is if you look around a certain value for a sample, you may or may not get the mean. And I already talked about this. 95% means there's a 5% chance that I'm going to fail. So suppose you gather sample 1, it falls right here, and you look 95% around it. And oh look, I managed to capture the mean. And then you gather sample 2, and you look 95% around it. Notice my mean doesn't fall in that interval, so I failed on the second one. And then the third and fourth I was successful as well. The problem with this is usually we don't know the population mean. We're just hoping that we're going to be able to do it at a level where we're confident that you will get to the mean. Now, if you're already wondering to yourself, why don't I just do 100% confidence level? Well, the Z star that goes with the 100% level of confidence is infinity, and that interval is useless. The terrible joke I like to make about this is it would be like your weatherman saying, hey, tomorrow the weather temperature is probably going to be somewhere between 0 and 200 degrees. It's not wrong, it's just not useful. So the problem is that if you use 100%, the interval becomes so wide, it's impossible to use it for anything. So keep that in mind. 100% kind of impossible. So there's a little bit of a catch-22 happening here. All right, let's start an example so we can actually build our first interval. All right, so assuming we have a normally distributed population for our credit card balances and a normal population and its standard deviation is equal to $400. So this is a big thing. I know sigma here. We don't always know this, so keep that in mind. That's the only reason this one's going to work the way it does. And I want to create and interpret a 95% confidence interval, construct. Anyway, for the population mean balance of a random sample, 100 accounts yields a sample mean of $200. So $2,000. So down here I've got a description of all of that for you. So I've got my sample mean, I've got my Z I'm going to use 1.96 for the reasons we've already described, I've got my sigma, and I've got my sample size. And so then I'm going to use this formula to create my confidence interval for a mean. So here's my point estimate, my sample mean, here's my critical value, because it's the Z-score that goes with going 95% in either direction, or sorry, around that value. So it gives me how far spread I am. And then right here is my standard error. Here's the size of my spread. So if you think about this as like, this is where I start, and then these two create how far I move in either direction to gather 95% of all values around my point estimate. Let's do it. All right. So we start out with our $2,000. We add and subtract 1.96 times my spread. So what I usually do is I will calculate this first, round it, and that is where you get the 7840 from. And then if you've never seen a plus or minus symbol before, what it means is you're going to go through and do the calculation once for minus, and then do it again for plus. So the plus one is always going to make the bigger of the two. The minus one is always going to make the smaller of the two. So I've written that out right here. So now that I know that's what this is going to be, here's my minus version, here's my plus version. Just keep in mind when you're looking at this to be careful as you calculate. Every time you round, or if you round a lot, you're going to be introducing error. Because this is money, I'm using 2 decimal places because that's traditional with money. Now, usually when we write this as an interval, we'll write it as the following. I'm about to write something I'm uncomfortable with. For some reason, your textbook uses a notation I have never seen before, and I don't really like. So it wants you to write $1,921.60, a big long dash, $2,078.40. I wanted to write this out because I wanted you to see it for the first time. So this dash I don't like because most people are going to look at it and think it means minus, and you'll subtract these two and get a number. That is not what it's doing. What they're trying to say is that this means 2. Like it could be any value between $1,021.60 up to $2,078.40. Sorry, $2,078.40. I could not get that out of my mouth. Yeah. They're using the long dash to hopefully make you recognize it is different from the subtraction. If that makes you uncomfortable, use the interval notation because that's what a confidence interval actually is. Okay, so to summarize what we just did, here you go. So this is how you write it with the big long dash. Fun times. Anyway, so what this tells us is I'm 95% confident that the population mean is somewhere between $1,921.60 and $2,078.40. Now this word, the population mean, is kind of like robotic. What you should be saying here is the credit card holders, or all credit card holders on average, will have somewhere between blah and blah. Because that's a little bit more accurate, a little more specific to the context of the problem. I like that description a lot better than just saying the population mean. Although that's what you're describing, it's a little bit better to include the context of what your variable is than to just say the population mean. Boredom. Alrighty, so there's one part of this structure that we haven't talked a whole lot about, and that's the margin of error. It's how far you're going in each direction, this guy right here. So the margin of error is simply your critical value times your spread that you're using for any confidence interval. And in this case, it indicates that your sample mean is, possibly within $78.40 of the population mean. The reason we want to look at margin of error is because if it's really large, that's a bad sign. We want it in general for it to be small because that means we're not off by that much. Remember, errors are how far off we are with our estimates, not wrongness. So we want a small margin of error so that we know we're fairly accurate. And we want a big level of confidence so that we can be confident with our estimate, or certain with our estimate. So you've got accuracy and certainty blopping around here. All right, let's build ourselves another one. Woohoo! So suppose we look at students' hours working at a university. So we're assuming these are student workers for the university, and they have a population with a standard deviation known to be 5 hours. We're going to construct a 90% confidence interval this time for the estimate of mean hours worked. And we've got a random sample of the students, and they have there's 64 workers with a mean equal to 23 hours. So once again, we're going to start by writing what we know. You go back to the slide where I had all of your critical values and look up the 90%er, it's 1.645. I know my population standard deviation to be 5 hours, and my sample size is 64. Now I'm going to take all those and plug them into the formula and calculate this. So here we go. Hopefully you can follow this okay. So here's where I place my sample, here's where I paste my z, and then these two work together to create the spread. If you calculate this together, you should get 1.03. At this point, I suggest you pause the video, pull out your calculator, and make sure that you get 1.03 when you do this. If not, we might need to talk about how your specific calculator will do these. Because the Windows calculator, if you're using it, is very, what's a good word for this? Picky. Yeah, picky. Picky's a good word. Picky about how it does the square roots in particular and how it does division and stuff. Yeah, it's a little weird, just so you know. You might want to consider buying yourself a 9-function calculator that has square roots and squares in it just for this. Don't go out and buy yourself a TI-83. That's completely unnecessary to just do a square root. Anyway, so when you calculate this, you'll get the following interval. So again, what I'm going to do is I'm going to take 23 and add 1.03 to it to get the upper interval. That one comes from the plus. And then if I take 23 and subtract 1.03, I get the lower part of the interval. So it looks like my possible range of values for the population mean is 21.97 hours to 24.03 hours. Fun times. Woohoo! Anyway, so if we calculate the margin of error for that, it comes out 1.03 hours. We saw that already. I don't know if I need to bother with it. So it tells me that when I look at my sample mean at 23 hours, I'm within about an hour of the true population mean by this estimate. Yeah. So if we take this same data and we change our level of confidence. So we started out with the 90%er. Let's go up to the 95. So you notice the only thing that changes is my z-star. And I'm also going to do 99. So we're increasing our level of confidence. Notice that that increases our critical value, our z-star value. And when you increase your critical value, look what's happening to our margin of error. It's getting bigger. So it appears that if we increase our critical value z-star, margin of error increases. That makes us less accurate. So this is what I was talking about when I said it's a little bit of a catch-22. At 99% level of confidence, I'm 99% sure I've got the truth. But I'm also the least accurate all of these because my error spread is much larger than the rest of them. Now in this case, because I have a fairly large sample, it's not that much larger. But if we were dealing with money and this was like thousands of dollars and you were only looking at something that was maybe worth $10,000, I would be concerned. All right, speaking of money, it's like I knew this was coming, hint, hint. Let's take a look at our first example. And here, I'm not going to change margin of error. I'm not going to change your critical value, so I'm staying at 95%. Instead, we're changing sample size. So we've doubled and then compared. So this is times 2. And then this is times 4. Woohoo. That looks horrible. Let's fix it. Sorry. Why is the eraser coming up again? Times 4. We usually use dot or star for multiply, not the cross symbol, because that also looks like an X. Anyway, so this first one is the one we did in the example. It's the one using 95% and a sample of size 100. So here's your $78.40. Hopefully he looks familiar. And then you look here and you're like, oh, it looks like my sample size, as it increases, appears to decrease my margin of error. So, and that makes sense. What am I really doing? I'm sticking a larger value in the denominator, which means that I'm dividing into more pieces, and the result should be a smaller piece. Cool. But here's the thing you might notice, depending on how good your math skills are. Compare these two. If I take 78 and do what to it, will I get 39? If you're having a hard time with the 78 and the 39, try it with just the last 2 decimal places. If I take 0.4 and divide it by something, do I get 0.2? Heck yeah. This is the same as divide by 2. So this was times 4, divide by 2. Why on earth is that happening? Well, I'm using 4 times as much here, but it's going into the denominator. Oh, look, and there's a root in the way. What's the square root of 4? It's 2. So I've done half as much in the denominator. And this is also a catch-22 here. Like, hey, if I want to have a smaller error, even by half, which is what we have happening for the first one versus the last one, the 7840 versus the 3920, I have to use 4 times as many people. I need a 4 times bigger sample. Yikes. So that's not a great way to reduce our margin of error, because then I have to survey a lot more people to figure out what's happening. Unless my data is easily accessible, this is a little bit of a bad plan. All right, so conflicting objectives. Dun, dun, dun. I want a small margin of error, but I also want a high confidence. And I also want a small sample size because sampling fewer people is cheaper. But all of these affect my accuracy. So I have to be careful in balancing the 3 of them together. Good luck. It's a hard road to travel. Anyway. So just to take a little break because we're about at the halfway-ish point. As a reminder, don't forget, point estimates are not great because they just give you one value. We're instead using the net of a confidence interval to get what I have. When I look at a margin of error, it gives me how far I possibly could go or how far off my sample might be from the true proportion. And it's the width of the interval, or width of half the interval rather. If I increase my confidence level, that'll increase my margin of error. If I increase my sample size, that decreases my margin of error. Ugh, I just realized that I read off the slides. I hate myself. Only a little though. In general, I'm pretty happy with me. All right. So what we're going to start doing now is, oh no, what if I have no idea what the population looks like? This is usually the sample, the state we're in at all times. Usually I have no idea what the population actually looks like when I'm gathering my sample. And that does change some things. So notice there's that S I was warning you about popping up. When you do this, you're going to be using the one from the sample instead. That's all this means. Just as a reminder, here's how you calculate a sample standard deviation. You can make Minitab do this for you. It's not such a big deal. Anyway, the big thing is that when you do this, you can no longer use the normal distribution because you have no guarantee that it will look normal. So instead, we're going to use what's called the student's t distribution. The student's t distribution is formed from using small samples and using the standard error. It was actually discovered by one of the guys who worked at the Guinness Brewing Factory because they needed to use small samples to estimate the alcohol content of their products. And in particular, they didn't want to use large batches and large samples because, well, then you had no product to sell. Pretty cool, huh? So beer made math. Fun. Oh, you may be wondering why it's called the student's t distribution. The guy who discovered its middle name was Student. So don't name your kid something kind of crazy. It might end up in history forever. We usually just call it tea. So we're spilling the tea today. Anyway. Some of the characteristics of the t distribution are that it almost looks normal, but not quite. So it usually has what we call like a peaky middle. It used to be called the witch's hat. It's usually a little pointier up here. Pointy. And it also has what we call fat tails. It's thicker out here because when you're using smaller samples, you're more likely to get unusual values than you would be with the normal distribution. It also used to be called the witch's hat because it kind of looks like that when it gets real pointy in the top. So there's that. Now, here's something else about the t distribution. The t distribution has a parameter of distribution. That means that it's not completely determined by its mean and standard deviation. It also has something else. It completely is different for every sample size you have. So if I did a sample of size 9 and you did a sample of size 10, we'd have different t distributions. That's how it accounts for all the small sample sizes. Whew. And the thing it depends on is what we call degrees of freedom. We've talked about degrees of freedom before, but we'll get into that. Come on. There we go. So degrees of freedom is just one less than your sample size. That's down here really low on the slide, so notice it. So what I've drawn here is the normal distribution along with two different degrees of freedom t distributions. So I've got the one for degrees of freedom 5 in the sort of darker green color. I tried to make this more appropriate for somebody who is colorblind, so I apologize if these colors are difficult for those of you to see, but hopefully these work better if you have color blindness. The lime green one is the one for 13. So notice degrees of freedom 5 is like way shorter, fatter, and longer, and has much bigger tails than the original standard normal, which is essentially a t distribution with degrees of freedom infinity, in case you didn't know. For those of you who know calculus, we say that t approaches z as degrees of freedom approaches infinity. Fun fact. They eventually look like each other is what that means in more common vernacular. But notice that even just stepping it up to 13, which is even that big of a sample size, that would be a sample size of 14, because 14 minus 1 would give me 13. I'm starting to get peakier. Notice like the top's getting closer, my tails are getting closer, these aren't that far apart. So it doesn't take that much for t to start to look like z. Usually you hit about 30, they're about the same anyway, so it doesn't matter. And you'll see that when you look at the t table. All right, so both are kind of bell-shaped, although not completely the same. One is the standard normal, and there are many t's. There's one z, but many t's. So much tea in the world. Let's drink it all. Anyway, and as I said, the t is more spread out, aka fat tails, yo. Yeah, let's take a look at this. So instead of using z, I'm going to be using t as my critical value, and that changes things. So since I'm using the standard error and using the sample standard deviation, I'm going to be using t with degrees of freedom of n-1. So notice there's no longer a z in here, it's a t. Now I know we spent a lot of time with the z one earlier. But to be honest, any of you who are going out and doing real math and real research are more likely to be using this. Usually we have no idea what our population looks like. This is the one you're going to use. Although we teach you both, this is the one you're going to use. All right, this is a horrible image, but here's the t-table. Yikes. So as you look along the side here, these are your degrees of freedom, which is n-1. And along the top here, there's a couple different things. Ignore these values. We'll get to those next chapter. But along the top, you have your level of confidences. And I'm going to show you how to read this. Confidence. That looks like not words. Oh well. Anyway, so for instance, if you wanted a 90% level of confidence for something that had degrees of freedom 10, you would be using this t value right here. That's so hard to read. I'm going to be much happier when we do the specific examples with this. Anyway, you'll notice that with these notes, there is the t table along with it. I copied it from your textbook, so it has a watermark on it to be aware of the fact that it belongs to Pearson, but it's still usable. Or if you want to, you can turn to the page in the textbook this is on and use it from there. Fun facts. Also, if you Google just T distribution table, you'll get these. There's tons of them. They used to sell whole books of them, because if you look down here, you'll notice it starts jumping into the hundreds, and people are like, oh my god, what am I going to do if I have 487 instead of 500? Well, you'd need a bigger table. It's a little annoying. I'm also going to show you how to get these on Minitab this week, so that'll be fun. Anyway, so let's do an example where we would use T. So, the distribution of overtime workers per week of employees at a manufacturing company is normally distributed. So I know it's normal, but I don't know the spread of the distribution, so I don't know sigma. Anyway, a random sample of 10 employees is selected, producing a sample mean of 4.5 hours and a sample standard deviation equal to 1.3 hours. Based on this information, construct and interpret a 95% confidence interval for the estimate of the population. So, yikes. I'm going to start out with what we know. We know the population mean, we know the degrees of freedom, one less than the number of employees. Since there were 10 employees, I'm going to be using 9. I know the spread of my sample, also known as little s, and I know the size of my population. I already said that one. Oops, size of my sample. So the next thing I need to do is I really need t. I need t95 with degrees of freedom n-1. I need this guy to be able to build my interval because I have everything else. All right, so here's my t table. So keep in mind, I want degrees of freedom 9, which is this row, and I want to do a 95% level of confidence. So I'm looking up here, 95. So I want to look down this column until I hit that row. Here we go. So this is going to be my t value, which I wrote right here a little bit clearer just in case this is a little too blurry for you. So I'm using 2.2622. Keep in mind when you're doing this, don't resist the urge to round this to like 2.3. You'll be a lot less accurate with that. Yeah, just don't do that, please. Anyway, so this looks the same. I'm going to start off with my sample mean, 4.5. Add and subtract my margin of error, which is going to be my t star times my spread. Remember, I'm using the spread of the sampling distribution because we're doing samples. I'm going to use 1.3, my sample standard deviation, because I do not know the population standard deviation. That's why I had to use t. And then I'm going to divide by the square root of my sample size. When you calculate that margin of error, you get 0.93. That's where this value is coming from. So then to build my interval, I'm going to take my 4.5 and add that to get the upper part of the interval and subtract my margin of error to get the lower part. When you do that, you get 3.57 hours on the subtraction and 5.43 hours on the addition. Again, I suggest at this point you pause the video, do this calculation yourself, and double check that you're able to get the same results I do. Whew. Based on this, we're able to say, hey, I'm 95% confident that the population mean of overtime hours is somewhere between 3.57 hours and 5.43 hours. So now I know how much overtime people are going to possibly get. That means that if you get somebody in your workplace that's getting like 9 hours of overtime, they're significantly different from the rest of the population. I'd be looking out. Something is rotten in Denmark with that one. Whereas somebody who is getting 5 hours of overtime, perfectly reasonable. All right, let's take a look at BMW crash damage because, yeah, it's going to be expensive. Anyway, so if you take a BMW automobile and crash it at about 20 miles per hour, the amount of damage that you do is the cost of the damage you do is normally distributed. Yay! So we're going to develop a 90% confidence interval based on a true population damage mean sample. So in this case, we only wrecked 8 cars. Notice how small that sample is. That's definitely going to be a T. Why? You don't want to wreck that many of your very expensive vehicles, right? This is completely reasonable and an excellent use of T. Anyway. So the mean sample damage is about $7,000 with a standard deviation of about $1,000. I don't want to read those numbers. Live with it. I've summarized the results down here. Notice that since there was only 8 cars crashed, my degrees of freedom is 1 less than that at 7. We're going to use these values to get our critical value for T and the fact that I'm doing a 90%er, and we're going to put them together into a confidence interval. Here we go now. Oh, that is so blurry. All I did was shrink down the other one and you can't even read it. Kind of hate myself. I don't know if it'll make you feel better, but doing these with Minitab is much easier than the table. And to be honest, like, I never use the table. I just make Minitab do them for me. I know that's horrible, but it's true. So if you can read that, in row 7, underneath the 90% confidence level column, which is the 6th one in, it's 1.8946. Open the one on your book that I gave you with these notes. It's a little bit easier to read if that's possible to look at both at the same time. Anyway, so I'm going to input my sample. There's my T value. Got to put this guy in here. So when you do your margin of error, it's about $758.93. That's this value. And then I'm going to add it to my mean to get the upper value. And I'm going to subtract it to get the lower value. So that's this step right here. That's all the plus or minus means. So that's going to be $6,491.07, or up to possibly $8,008.93. And just as a reminder, your textbook would write this as 6491.07, a giant dash symbol, and then the lower one. I can't fit the $sign on the first one because I screwed up and wrote it too far over. It gets cut off. And remember, this just means 2. It's values in between those two. So if I was to interpret this interval, I'd write, based on the sample data, I'm 90% confident that the population mean damage is somewhere between $6,491.07 and $8,008.93 for BMWs. I should have included that, because that's a little more specific. Obviously, if you drive a kind of crappy Ford like me, your damage is probably going to be less. Just saying. Yeah. My brother-in-law has one of those. It's a nice car. Yay, BMWs. Sorry. Okay, so remember our conflicting objectives: high confidence level, low margin of error, small sample size. This is a little bit of a problem. Remember, T is going to be a little bit more wobbly or possibly larger because of that, but sometimes you'll have no choice but to do a small sample. That's just how it is. Think of the beer example. I don't want to waste my products. Think of the cars with the BMWs. I don't want to wreck all my cars. Oh, that sounds very expensive. Oh no, there goes my voice. Oh, I did that into the mic. And I can't edit on this version of video recording. I'm going to regret that later. Anyway, now let's look at how can I try to control the size of sample I'm going to be doing. So the idea is that a lot of companies, what they'll do is what's called a pilot study, where they'll do a small sample, see what the results look like, and then release on a bigger sample once they know how big they might want to be to have a small margin of error. So I'm using E for margin of error. That is not a traditional symbol for this. Usually we use ME for margin of error, but we're going to use E because, well, it's one symbol instead of 2, so that should make it easier. So what we're going to do is we're going to say, hey, if I know how big I want my error to be, like say I want it to be within $100 instead of $700 for the cars, I know what my spread is and I know how confident I want to be, and that tells me my z-score, I can find my sample size. So what I'm going to do is I'm going to take this and solve for n. So I'm going to write it over here. E equals z times sigma over the square root of n. So the first thing I'm going to do is divide both sides by z. Z divided by z is 1. That's silly. So I've got ez equals sigma over the square root of n. I know I'm trying to solve for n, so I'm going to cross multiply. So that'll give me e square root of n equals z times sigma. In case you forgot how cross multiplying works, you just multiply these two equal to multiply those two. All right, so again, remember your goals. I want to solve for n, so now I'm going to divide by e. E divided by e gives me 1. That's essentially multiplying by nothing. So now I'm left with square root of n equals z sigma over E, and then to get rid of the square root, I'm just going to square both sides. So that gives me that n is equal to, I'm trying to make this fit now, z sigma E squared, and if you remember your rules of exponents, I can distribute that exponent, z squared sigma squared over, oh, that's supposed to be a sigma and I wrote it as an E. We'll just fix it and pretend I didn't screw up, okay? Sigma squared, which if you look back here, that's that formula. Fun times. So just to give you an idea of where that comes from, that's the whole purpose of this. So if you solve for n and you have some idea how big your error you want it is to be, you can definitely pick what sample size you want. Now most places, because they know ahead of time they're not going to get everybody to be a part of their sample, usually what they'll do is they'll plan for a little bit bigger than what we have. So you'll see me do that here in a minute in my next example. All right, so suppose emergency medical response unit in major U.S. city is interested in estimating the mean response time to an emergency call. The times are assumed to be normally distributed. They know from a previous example usually that the standard deviation tends to be about 2.5 minutes. If the agency wishes to develop a 95% confidence estimate for the interval and they want to be within 0.5 minutes, find using the margin of error, what sample size will they need? So in particular, since it's a 95% interval, that tells me my z-value is 1.96. I know my spread, and I know how far I want to be for error. So if you just take those and plug them into our formula, you get the following. Can you see my mouse? There it is. And you get this fraction in the middle. And then if you calculate that, you'll get 96.04. We're going to round that up to 97 because we want to be within or less than, sorry, we want to be within 0.5 minutes. So we want to round up because we know that n goes in the denominator. So if I pick a larger denominator, I will end up with a smaller error versus if I picked a smaller denominator value for n, I would end up with a larger error. So if we're willing to accept 0.5 minutes, slightly smaller would be better, slightly bigger would not be. All right. Let's do another example. So suppose we're looking at the American Dairy Institute. Yay, moo cows. Sorry, I used to live in Wisconsin. We wish to develop a 90% confidence interval for the mean estimate of the number of gallons of milk consumed by per family of 4 in the U.S. This is actually something they estimate every year. Fun fact. They wish to estimate within 3.5 gallons, so they create a population standard deviation in a pilot sample of just 50 families. So there we go. There's that pilot study, the initial study to figure out how big they want it to be. And they have a sample standard deviation of 62.5 gallons. It's a very large standard deviation. I almost don't trust these numbers, even though I got them from the American Dairy Institute. And usually they're pretty accurate. That's really large. It's a big spread. I should have picked a... Okay. Anyway, so again, this z value I just took from that table because I am using z because I know my population standard deviation is 6.25. So in particular here, you'll notice I'm using s, but I'm still using z because without the sample size n, I can't use t. And then here is my error. I want to be within 3.5 gallons. So my error goes down here, my z goes here, and my sigma goes here. We're going to square all those and then do some division, and you'll get 862.89 people. We're going to round that up to 863 people. Now, since they already have 50 families from the pilot study, what you can do is count those 50 and instead sample only 813 more to get to the error you want. The reason why this one is so large is because of how big the spread is and how small they want the error to be. That's a lot to ask. There's a very small error compared to the spread. Whew. I don't know who thought of this one, but that's a lot. That's a lot of people's. But again, America is quite a big place with a lot of variation. It's not unreasonable to do a large sample like that when you're trying to do a whole country, especially when it's this size. All right, so what affects sample size? Your level of confidence, your margin of error, and your population variation, aka your spread or sigma. So sigma, E, and level of confidence making z. Please notice we're always using z for this, not t, because without knowing sample size, you can't get t. Always z when it comes to calculating sample size. Polite reminder, sample size is little n. That looks like a squiggle. Little n. I didn't make it better. Junk. All right. Last up, let's do the same dance, but for a proportion. So in case you forgot, when it comes to calculating a proportion, I always take and add the number of items I'm interested in out of my total population to get a proportion proportion. Proportions are always between 0 and 1 because they're made from a fraction and counting. Oh, I might be forced to use the standard error for this. So keep in mind, I might be stuck doing this guy as well. So, or if I don't have any idea what the population looks like, I might be doing p-bars in this. So don't forget that. I have that written right below and forgot I did. That's awesome. Or that guy. Or you might be stuck with using the sample one. Remember, as long as my sample size is sufficiently large, this looks normal. If it looks normal, that means I can do the sampling distribution estimates on this and therefore build myself a confidence interval. Only this time it's called a P, or a proportion. All right. So here's the sampling distribution for a proportion. So this is our center, and then we're going to use the spread. So just like you saw me do with means, we're going to go so many standard deviations away, like maybe it's 2, and build our confidence interval around it. So how many I do, that's a z-value, times my spread to get the upper and lower edges. So this will be p-bar minus z times the square root of p-bar. I should have just wrote standard error times 1 minus p-bar. Too late now for n. We'll do it for the other one too. And then this will be p-bar plus my z star times my p 1 minus p spread. Yeah, spread. One thing nice about p and doing proportions is it's always going to be a z. There's no t nonsense. All right, so suppose we have a company that's interested in estimating the proportion of a population who will redeem a coupon that they offer in the mail. This is a typical use of this. These are called mailing studies. A random sample of 100 individuals are being selected to receive a coupon, and 22% redeem that coupon. Sorry, 22 of them redeem that coupon. 22 out of 100 is 22%. That's my bad. Anyway. Develop and interpret a 99% confidence interval for the estimate of the population proportion. So I was doing this when I first saw that 22. I was like, hey, well, I've got 22 out of 100, and that's going to be 0.22. And then I'm going to use that to build my whole interval. So this 2.575, that's for the 99% confidence interval. That's based on the 99% z-score value. Remember 0.22, that's the p-hat value. It shows up here and here, and be careful. 1 minus p, that's 1 minus 0.22 gives you 0.78. Sorry, I'm just trying to explain where all these values come from. I think I just accidentally hit end show. Nope, okay. So you plug all those values in. When you calculate this, you get up just shy or just over 10%. I almost said just shy of 11%, but just over 10%. That's kind of a big margin of error. It's almost as large as the item itself, so that makes me upset. So what you'll do is, just like you've seen before, I'm going to take 0.22 and add the 10-ish% to it to get the upper value, and then subtract to get the lower. So it's somewhere between 11.33 and 32.66. So how we'll describe that is we'll say we're 95% confident that the population proportion that will redeem the coupon for this store in particular appears to be between, and normally I would write this as a percentage, 11.33% and 32.67%, but here I've written it as a proportion, so it's a decimal. Be careful, this is not a probability. That's different. All right. So similarly to what we did with the means, you can also estimate sample size for a proportion. If you take the margin of error equation, E equals Z times the spread, and solve it for your sample size n, you get the following equation. I'm not going to write this one out because I don't feel like it. Anyway, you get the following equation, and you can use that to estimate the population size you need. We're going to do the same thing. We're going to estimate a population based on it. All right, so if you take an advisor of a political campaign and you want to see, based on a poll, if people are likely to vote for her candidate, so she develops a 90% confidence interval with the estimate of the margin of error to be 2%. So notice here, all you need is 90% confidence and margin of error. What we're going to do here that's a little unique is we're going to use a specific proportion that will give us the maximal value for any interval. So down below, sample size. You'll notice I'm going to be using p equals 50%. This is important, so like put hearts and stars and whatever in your notes that makes you indicate that you know this is important. When you don't get given a proportion, you'll always use 50-50 for it when it comes to calculating sample size, because it'll give you the biggest sample size. This is the z-value that goes with 90%, and then here's the margin of error that they gave us. We're going to plug those into this formula, and you get the following. And if you calculate that, hey, I get like this number. You might want to take a minute to calculate this one to make sure you get the same thing I do. When you do that, make sure you round up like always. We're always going to round up with this value, not round down, because it'll put us closer to having the margin of error that we want or below the margin of error that we want rather than above it. Okay, so what does that mean? Well, if she wants to be that sure, 90% and within 2%, which is really small, she needs to sample like 1,692 people. When it comes to doing polls, especially political polls, in general, anywhere from 3 to 5% is what most people want for polling. 2% is a little extreme. Anyway, so suppose a market research firm wishes to develop a 95% confidence interval for the estimate of the proportion of customers in the market area that they will have in favor of a real response for their advertisement. So who's going to say, hey, your stuff looks good? They want to estimate with a margin of error of about 0.015, another really tiny one. What was I thinking when I wrote these? Anyway, oh no, I got this one from your book. I'm a cheater. Anyway, got to cite my sources where necessary. Hey, Pearson, thank you. Anyway, they want to estimate their margin of error within this 1.5%, which is insanely small. They do a pilot sample of 40 people and they found 33 favorable responses. How many additional people should they survey? So we start with estimating our p-hat value, which is the 33 that said yes out of 40. That gives me the following. That's pretty large. And then here is my Z value, 1.96, which we've used like 4 times, so you're kind of used to that guy. And here's my margin of error. So big thing, notice I'm not using 50-50 since I have a pilot study. Not 0.5. Anyway, so we're going to plug those values into the equation, and we'll get 2,466. Since I can use those 40 people I've already asked, we'll subtract that to get the net sample size of how many I need to sample remaining to get the proportion that I want. All right, so we've learned a lot. We've done point estimates. We've done 3 different types of confidence intervals. We've done T's and Z's for means, and we've done a Z for proportions. Yikes. We've also talked about how to find sample size for each of those. There's a lot going on, man. Oh boy. Please notice that when it comes to doing sample size, I need to have an estimate for the margin of error. So anytime you see a question where they give you the margin of error first, you should be thinking, I'm going to be finding sample size. Bam. That's how you tell those away from the rest of those. Yeah. Anyway, that's one of the bigger questions I usually get asked by students. How do I know when I'm going to do this? If they give you margin of error, every time. That's it. Since I did use some of Pearson's stuff, keep in mind, you shouldn't disseminate this to other people. Fun fact. I don't know. I always hate that I have to throw in this disclaimer if I use their stuff. And that's it. Thanks for listening.